Welcome to the Deep Dive, the place where we transform complex research stacks into clear, powerful knowledge, really custom tailored for you. Today, we're undertaking a pretty crucial mission, grounding ourselves in the essential mathematical and algorithmic foundations of reinforcement learning-RL. This is the tech that's becoming the backbone for next-gen autonomous cyber operations.
Absolutely. This really is the starting point. If you, listening right now, want to get how these sophisticated agents can learn to do complex stuff, automated pen testing, finding 0 days, simulating advanced threats, well, you first have to master the language of the Markov decision process and the logic of the deep learning algorithms that kind of interpret it.
Precisely. RL isn't just in the lab anymore, is it? It's moving to the front lines. It's acting as a critical force multiplier. I mean, as cyber threats get faster and more complex, the only real answer seems to be using AI to combat AI. And that means deploying machine learning techniques so, a small team can have a huge impact.
So our journey today, we're going to stick really closely to the structure of the source material. We'll kick off with the mathematical framework, the Markov decision process, or MDP. That gives the agent its boundaries, its structure. From there, we'll move into the core things the agent learns, the learnable functions, policies, value systems, and how it models the environment.
And then finally, we'll tackle the modern heavy hitters, the deep reinforcement learning algorithms that make this all work on large-scale network data. We're talking deep Q networks, DQN, then the more refined advantage actor critic, A2C, and the current benchmark for stability and performance, proximal policy optimization, or BPO. Understanding this progression is really understanding the power behind automated intelligence. Okay, so let's start with this core dilemma in training any intelligent agent, the just overwhelming computational burden of history. If we wanted an agent to build like a perfect traditional policy, a set of rules for every possible situation, you'd instinctively think it needs to consider the entire history, every state, action, reward it's ever seen to decide the next move.
And that approach, well, is basically doomed from the start. Imagine an environment where just one operation, one episode, could stretch over, say, tens of thousands of time steps. Trying to base a decision on that potentially infinite history. The transition function becomes impossibly complex. The computing power needed just explodes, and the training itself, completely unstable.
It's that problem of history overload. The taxi driver analogy in the sources is great for this, isn't it?
Yeah.
Imagine being a taxi driver, and before deciding where to go now, you have to pull up this massive, years-long record of every single pickup, drop-off, weather condition right back to day one. You just sit there.
Exactly. You'd be completely paralyzed by all that information. The complexity of modeling the environment, accurately predicting what happens next, it's directly tied to how much history you're conditioning on. If that history is huge, the problem just becomes infeasible, both mathematically and practically.
And this is exactly where the solution comes in, the Markov property, which leads us straight to the Markov decision process.
The Markov property is this really powerful simplification. It essentially says that for figuring out the next state, self 1 plus 1, you can effectively forget the past. All the agent needs is the here and now, the current state, sest and the action it just took, 8t.
So that formal bit, dest plus 1 sim, pst plus 1 spate, that just means the next state comes from a probability distribution based only on the immediate last state in action. No need to look back hundreds of steps.
Precisely. That massive reduction in what needs to be considered is what makes RL actually workable. But, and this is a really crucial point, especially for building cyber agents, the environment has to be set up so the current state actually holds all the necessary information.
So that's the engineering challenge then. For the taxi driver, the state needs to include not just location, but maybe time of day, local events, things like that. If you leave out the time and the agent thinks it's dinner rush at 3 a.m. in the restaurant district, well, the Markov property is broken because the state wasn't complete. It leads to bad decisions.
Right. And if you translate that to a cyber operation, the state of the network at time needs to be really rich. It needs the topology, discovered services, the agent's current privilege level, vulnerability status of hosts. If the agent only knows its current location on the network, but not, say, its privilege level, it can't make a smart choice about which exploit to try next. The state description was insufficient.
Okay, so the MDP provides this formal structure for the environment. It's usually described as a tuple of components. Let's break down that structure.
Okay. First up, you have the set of states.
Yeah.
These are basically all the possible descriptions, all the snapshots of the situation the agent could be in. In a cyber context, S could be huge, right? Covering the status of thousands of machines, compromised, reachable, resources discovered, and so on.
Got it, states. Then second, the set of actions, A. These are the choices the agent can actually make in any given state, and they need to be well-defined actions. For the taxi, turn left, wait. For the cyber agent, it's things like scan the specific subnet, try this specific exploit like MS-17-010N, or attempt privilege escalation technique X.
Third, and this one's really key, the transition probabilities. This is what brings in the real-world messiness, the uncertainty, the stochasticity. It models the chance that if you take action A in states errors, you'll actually end up in a specific next state citillars. It's not always guaranteed.
And why is modeling that uncertainty so important? Why not just assume things work?
Well, if transitions were totally deterministic, always 100% predictable, the agent could just map out the perfect path from the start. It wouldn't really be learning. It'd be more like solving a maze. But in the real world, especially in CyberOps, things are fuzzy. Network lag might cause a timeout. A defense system might randomly trigger. An exploit might only work, say, 70% of the time. The transition function P captures that inherent unpredictability of the environment.
Okay, structure makes sense, but we need a goal, right? A definition of success. That brings us to the objective function and rewards. The agent's whole point is to maximize its total expected reward over some sequence of actions, a trajectory tau.
Right. And initially, you might think the objective is just, sum up all the rewards, sum to tau, just add up everything you collected during the operation. But, as the source material points out, that simple sum misses a crucial element. The time value of reward.
Ah, yes, the idea that getting a big reward now is usually better than getting the same reward way off in the future. Delayed gratification, basically. We need to formalize that.
And that's done using the discount factor. Gamma is just a number between 0 and 1. It basically controls how much the agent cares about future rewards versus immediate ones, how far-sighted it is. So the formalized objective, the thing we actually want to maximize, becomes the cumulative discounted reward.
And the clever part there is that as the time step t's gets bigger, that reward toters gets multiplied by gamma rays to the power of t.
Oh.
Since gamma is less than 1, that fraction gets smaller and smaller. Distant rewards just become worth less.
Exactly. And this is where tuning gamma becomes really interesting for modeling different kinds of adversaries. If you set gamma really close to 1, like 0.99, the agent becomes highly farsighted. It's willing to put up with, say, 100 steps of getting almost no reward if it leads to a massive payoff way at the end. This mathematically models a patient, stealthy attacker, maybe a nation-state actor, who prioritizes the long game and avoiding detection.
Right, but if you tune gamma way down closer to 0, maybe 0.1.
Then the agent becomes extremely nearsighted. It only cares about immediate gains. It'll grab the first obvious vulnerability for a quick win, even if that totally blows its cover or ruins the chance for a bigger prize later. That models a less sophisticated smash-and-grab type attacker. So just tuning this one parameter, gamma, is incredibly powerful for simulating or even defending against different adversary profiles, #tag2, learning how to be an agent. 3.3 learnable functions for agents.
Okay, so we've laid out the rules of the game with the MDP framework. Now let's shift gears from the environment structure to what the agent actually has to learn to operate successfully within it. The sources lay out 3 fundamental ways an agent can figure out how to behave optimally.
These 3 functions, policy, value, and model, they're like the different blueprints the agent can use to turn that raw MDP math into an actual working strategy.
First up, we've got the policy model 3.3.1. This feels like the most straightforward approach. Just learn the optimal guidebook directly.
Yeah, you can think of a policy, usually written as Babel, as that direct mapping. It tells the agent, okay, you're in state, the best thing to do is action another. Now, in DeepRL, this policy is often represented by a neural network. And crucially, it usually outputs a probability distribution over all the possible actions given the current state.
That stochastic part, the probabilities, that's important, isn't it? It means the policy doesn't just rigidly pick the single best action every time.
Exactly. That randomness, that stochasticity is vital for exploration. It stops the agent from just getting stuck doing the first thing it found that worked reasonably well, which might not be the actual best strategy. The policy model's goal is to directly find the policy power that maximizes that expected cumulative discounted reward we talked about.
Well, yeah.
This is really the heart of what we call policy gradient methods, which we'll definitely circle back to.
Okay, policy model learns the how-to. The second approach is the value-based model, 3.3.2. This one seems to shift focus from direct instructions to more like a rating system for states or actions.
That's a great way to put it. Instead of a guidebook, this learns value functions. These functions assign a score, quantifying how inherently good or valuable it is to be in a certain state or to take a certain action from that state. It's all about potential future earnings or rewards. And this is super useful because it lets the agent evaluate situations even before it's figured out the perfect step-by-step policy.
Let's quickly clarify the two main types of value functions here because they sometimes get mixed up.
Good idea. First, there's vivassess, the state value function. This estimates the total expected discounted reward you'd get if you started in state CSALers and then just followed your current policy from that point onwards. It's like the inherent value of that state itself under that policy. Then there's CASES, the action value function, often just called the Q value. This estimates the expected discounted reward if you start in state, take a specific action adder, and then follow policy tail afterwards.
Okay, let's use the taxi analogy again. The state dollars of being near a concert venue right when the show lets out, that state probably has a really high vials, right? Because the potential for fares is huge no matter exactly what you do first.
High intrinsic value.
But the Q function compares the agent compares specific choices in that state. Is the value of action, $8 waiting right by the exit for 10 minutes, higher than action Pierre Joe driving around the block looking for fares? The Q value gives a score to the combination of being in that great state and taking that specific action.
That distinction is absolutely critical, especially when we get to algorithms like DQN, which are entirely built around learning and approximating these Q values. Because if you have accurate Q values, choosing the best action is easy. And spade of filers just pick the action that gives you the highest Q and a high phi.
Makes sense. Okay, that leaves the third approach, and maybe the most ambitious one, model-based learning, 3.3.3.
Right. This is where the agent tries to go beyond just learning what to do, policy, or how good a situation is, value. It actually attempts to build its own internal simulation, its own predictive model of how the environment works. This internal model tries to predict the outcome. Given I'm in state RLs and I take action intervals, what's the likely next state round T plus, and what reward ARDAs will I get? It's learning the environment's dynamics, like the transition probabilities P we discussed.
And what's the big advantage of having this internal simulator? What does it let the agent do that the other approaches don't?
The huge payoff is the ability to plan. Once the agent has a reasonably good internal model, a kind of digital twin of the network or environment, it can play out scenarios in its head. It can simulate sequences of actions and see their likely outcomes multiple steps into the future without actually having to interact with the real, potentially slow or risky environment. It can run thousands of virtual what-if scenarios, try this exploit, scan that range internally, and then just execute the single sequence that looks most promising in the real world. This can massively speed up learning, improve sample efficiency, and is especially powerful for complex long-term tasks, like planning a sophisticated cyber attack campaign, #tag3, deep reinforcement learning, DRL, and deep Q networks, DQN.
Okay, so those foundational ideas, MDPs, policies, values, models, they're critical.
Yeah.
But they often hit a wall when faced with the sheer scale and messiness of real-world data. I mean, when your state isn't just a few grid locations, but maybe millions of pixels from a screen or data from thousands of nodes on a network, those simple table-based methods just completely break down, don't they?
Absolutely, they just don't scale. And that's precisely where we need the power of deep reinforcement learning, or DRL. DRL is essentially the marriage of deep neural networks with that RL framework we've been discussing. For things like autonomous cyberops, the inputs are often enormous and complex. Think network scans, system logs, telemetry data, vulnerability reports. High dimensional doesn't even begin to cover it. Neural networks are indispensable here. They have this incredible ability to process that sheer volume of data, automatically extract complex, relevant features, and spot patterns that simpler models would completely miss. They allow RL to generalize.
Right. And the basic training loop looks familiar if you know standard deep learning. You do a forward pass to make a prediction, calculate a loss based on how wrong you were, and then update the network's weights using something like gradient descent, and repeat. But plugging neural networks into the RL setting throws up some unique and tricky challenges.
Oh, definitely. The first, and maybe the biggest difference from supervised learning, is the lack of an explicit correct answer. In supervised learning, every input comes with a nice clean label saying, this is the right output. In RL, the agent only gets sparse, often delayed feedback in the form of rewards or punishments. This creates that tough credit assignment problem. If you finally get a reward after a long sequence of actions, how do you figure out which specific action, maybe one you took 100 steps ago, was actually responsible for that success?
Yeah, that sounds hard. And then there's the classic exploration versus exploitation dilemma we touched on earlier.
Mm-hmm. The agent is constantly facing this trade-off. Should it explore, try out new actions it hasn't done before, which might lead to discovering a much better strategy? Or should it exploit, stick with the actions it already knows produce reasonably good, reliable rewards, even if they might not be the absolute best? Finding the right balance is crucial. Explore too little and you get stuck in a rut. Explore too much and you waste time on suboptimal actions instead of racking up rewards.
And there's another fundamental issue with the data itself, right?
Yes, the data problem. The experiences the agent collects as it interacts with the environment, REST at RT plus $1, are highly sequential. The state at time 10 plus $1 is heavily dependent on the state at time tailors. This means the data samples are strongly correlated. But standard deep learning training techniques usually assume the data points are independent and identically distributed IID. Violating this IID assumption, which RL interaction inherently does, can make the neural network training process really unstable and inefficient.
Okay, these challenges, sparse rewards, exploration, exploitation, correlated data, they set the stage perfectly for the first big breakthrough in DRL, the Deep Q network, DQN. Let's walk through that implementation, maybe using the classic example.
Right, the carpool benchmark is the perfect illustration. It's simple, but captures the core ideas. The goal is to balance a pole upright on a moving cart. The agent can only push the cart left or right. It gets a small reward, +1, for every single time step that the pole stays balanced within certain angle limits. The episode ends if the pole falls too far or the cart goes off the track. The Q network's job is to learn, for any given state, cart position, cart velocity, pole angle, pole tip velocity, the expected future discounted reward, the Q value for pushing left versus pushing right.
And the DQN architecture itself. Since the state isn't just a simple grid location anymore, it uses a neural network to approximate that Q function, right? Instead of big table mapping states to Q values.
Exactly. For a carpool, the state is just those 4 numbers. So the network might be relatively simple, maybe just a couple of fully connected layers, like in figure 3.4 in the sources. It takes the state vector as input and outputs 2 numbers, the predicted Q value for moving left and the predicted Q value for moving right.
But, as we just discussed, training this network directly on the sequential LAGR experiences leads to instability because of the correlations. So DQN introduced a really clever fix.
Yes, the key enhancement, the replay buffer, or experience replay, ER. This was a major innovation.
How does that replay buffer actually work? What's the mechanism?
It's pretty straightforward conceptually. You create a large memory buffer, like a big list or queue, that stores past experiences as the agent interacts with the world. Each stored item is typically the tuple, ET at AAT +1 at text done flag. Then, when it's time to train the Q network, instead of just using the very last experience the agent had, you sample a random mini batch of these tuples from the replay buffer. You might grab, say, 32 or 64 experiences randomly from the last 10,000 steps stored in the buffer.
And the magic is in that random sampling from a large history.
Precisely. By sampling randomly, you break the strong temporal correlations between consecutive steps. The mini-batch contains a diverse mix of experiences from different times and different parts of the state space. Suddenly, the data being fed to the neural network for training looks much more like the IID data that standard optimization methods like stochastic gradient descent expect. This massively stabilizes the training process. It stops the network from catastrophically forgetting past useful experiences or getting stuck chasing the latest, possibly noisy interaction. It's like shuffling a deck of cards before dealing.
Makes perfect sense. So the buffer tackles the correlated data. How does the agent actually choose which action to take at each step, balancing exploration and exploitation? The sources mention a Boltzmann policy in figure 3.5.
Right. While simple epsilon greedy, mostly pick the best action, sometimes pick randomly is common, a Boltzmann policy offers a slightly more nuanced approach to action selection. Instead of a hard switch between best and random, it selects actions probabilistically based on their current estimated Q values. Actions with higher Q values are more likely to be chosen, but actions with slightly lower Q values still have some chance of being selected. The temperature parameter in the Boltzmann distribution controls how exploratory it is. High temperature means more randomness. Low temperature means it mostly picks the best action. It gives a smoother exploration strategy.
Okay, so the overall DQN picture is use a deep neural network to approximate the Q function, use a replay buffer to store experiences and sample randomly for stable training, and use a policy like epsilon greedy or Boltzmann to select actions. The result is a learned Q network whose parameters implicitly define the optimal policy, allowing it to tackle complex tasks. But you mentioned a limitation. It learns the policy indirectly through the value function. Does that cause problems sometimes?
It can, yes. The main area where this indirectness becomes a bottleneck is in environments with continuous action spaces. Think robotics, where an action isn't just left or right, but setting a joint angle to any precise value within a range, or adjusting thruster power. In those cases, finding the action A that maximizes USI requires an optimization step itself at every decision point, because you can't just check a few discrete options. That becomes computationally very expensive or even intractable. This limitation, the difficulty with continuous actions and sometimes instability, is exactly what motivated the development of methods that learn the policy more directly, namely actor-critic methods, #tag4, advantage actor-critic ADC, right? Which brings us neatly to advantage actor-critic ADC. ADC represents a really significant step forward because it explicitly separates the job of learning the policy from the job of estimating value. It uses two distinct components, the actor and the critic.
Okay, so instead of one big network trying to figure out Q values, which implicitly define the policy, we now have two specialized networks, or at least two specialized heads on a shared network. One decides what to do, the other evaluates how good the situation is.
Exactly that. A2C tries to combine the best features of both policy-based methods, which handle continuous actions well, and value-based methods, which tend to be more sample efficient and stable thanks to learned value estimates. This separation generally leads to more stable training and better performance, especially in complex environments, compared to earlier policy gradient methods or even vanilla Q learning.
Let's break down those two components then. First, the actor, 3.6.1. The policy learner. What's its specific job?
The actor's sole focus is on learning the policy itself, usually denoted PETA, where theta represents the parameters of the actor's neural network. Given the current state, the actor outputs an action, or more commonly, a probability distribution over possible actions. It learns using the policy gradient approach we hinted at earlier. The core idea is to adjust the policy parameters theta in a direction that increases the probability of taking actions that led to better than expected outcomes.
And mathematically, that update involves the gradient of the policy, nabla theta, multiplied by some kind of signal indicating how good that action all was in state, which is where the other half comes in, right?
Precisely. The actor needs to know how much better or worse that action was compared to just sort of the average outcome from state sellers. That crucial signal is provided by the critic and the advantage, 3.6.2.
So the critic's job isn't to choose actions, but just to evaluate the current situation.
Correct. The critic learns the state value function, via star. Its network takes the state val as input and outputs a single number estimating the expected total discounted future reward from that state onwards, assuming the actor's current policy suspecha is followed.
Okay, and how does that state value, dollars is dollars, help the actor learn better? How do we get that better than expected signal?
That's where the advantage function valors comes in. This is arguably the core concept that makes actor-critic methods work well. The advantage function measures the relative value of taking a specific action in state dollars compared to the average value of just being in state dollars. It asks, how much better or worse was taking action at dollars than what I would typically expect to get from this state at doll?
And the calculation for that is a day, or SPD SBT tells us the value of the state action pair minus the value of the state itself. Why is that subtraction so important?
That subtraction using $5 as a baseline is absolutely key for reducing variance and stabilizing learning. Imagine the agent happens to be in a really good state. Maybe it just compromised a key server, so $5 is very high. Now, let's say it takes an action that's actually pretty mediocre, like running a slow, noisy scan that doesn't reveal much. The immediate reward might still be slightly positive just because it's in a good spot. If the actor only learned based on the raw reward or the raw Q value, it might mistakenly think that mediocre scan was a great action.
I see. But because we subtract the high baseline value, if QSUS is only slightly higher than VITAS, the resulting advantage will be small. Or if QSUS is actually lower than VITAS, meaning the action was worse than average for that state, the advantage will be negative.
Exactly. The advantage tells the actor whether the action taken was genuinely better or worse than the expected baseline for that state. It provides a much cleaner, lower variance signal for updating the policy. This makes the learning process far more stable, especially in environments where rewards are sparse or noisy, which is very common in cybersecurity tasks. The critic's learn a value function provides that crucial dense feedback signal, even when explicit rewards are rare.
Okay, that makes a lot of sense. So when it comes to actually implementing A to C 3.6.3, how does the network architecture typically look, reflecting this actor-critic split?
Often you'll see separate neural network classes defined for the actor and the critic, as shown in Figure 3.9 of the sources. The actor network needs to output an action distribution, so its final layer might be a softmax for discrete actions, or parameters for a Gaussian distribution for continuous actions. The critic network just needs to output a single scalar value representing byboards, so its final layer is typically linear. Sometimes the initial layers that process the raw state input might be shared between the actor and critic networks to save computation, with separate heads branching off for the policy and value outputs.
And the training process often involves something called the Generalized Advantage Estimation, or GAE function, figure 3.2. That sounds like another layer of refinement on calculating that advantage signal.
It is, exactly. Calculating the true advantage Q's errors can be tricky because we usually don't know the true Q values. We have to estimate them. GAE provides a sophisticated way to estimate the advantage that tries to balance the trade-off between bias and variance. Simple one-step TD errors, looking just one step ahead, have low variance but can be biased. Longer-term Monte Carlo returns, looking all the way to the end of the episode, are unbiased but have very high variance. GAE, using a parameter lambda, cleverly blends together TD errors over multiple prime steps. It allows you to tune this bias-variance trade-off.
So essentially, GAE looks at a whole sequence of immediate rewards and value estimates to get a more stable and accurate estimate of the advantage the $80 for each step.
That's the core idea. It uses this weighted sum of TD errors to provide a more reliable target for the actor to learn from. It smooths out the noise and helps the policy converge more reliably. The overall A to C training loop then involves collecting a batch of experiences, states, actions, rewards, next states, using the critic to estimate values dollars, calculating the advantages, often using GAE, and then using those advantages to update both the actor's policy parameters to make high advantage actions more likely, and the critic's value parameters to make its value estimates more accurate.
Okay, so A to C with GAE sounds like a pretty solid improvement, separating actor and critic, using advantage for stability. But even with these advances, policy gradient methods can still sometimes suffer from a major issue, taking too large an update step. If one update drastically changes the policy, it can actually make performance collapse, right? The agent forgets everything good it learned and ends up in a terrible part of the strategy space, potentially taking ages to recover.
That's exactly the problem PPO was designed to solve. Proximal policy optimization, or PPO, has really become the go-to algorithm in many practical RL applications for this very reason. It's renowned for hitting a sweet spot. It converges quickly like some other methods. It's remarkably stable during training, and it's relatively sample efficient. It builds directly on the ideas of actor-critic and policy gradients, but adds a crucial mechanism to prevent those destructively large policy updates. It came about as a simpler, often better-performing alternative to an earlier method called Trust Region Policy Optimization. TRPO.
So the core idea behind PPO is control. Keep the policy updates proximal, meaning close to the previous policy, to avoid those catastrophic jumps.
Precisely. We want to improve the policy, yes, but we need to do it cautiously. PPO achieves this control by modifying the objective function that the actor tries to maximize. Instead of just maximizing the advantage-weighted log probabilities, it optimizes a special clipped surrogate objective function. This modified objective mathematically limits or penalizes policy changes that would cause the new policy to deviate too much from the old policy within a single update step.
And the sources mentioned there are two main flavors, or ways PPO implements this control mechanism.
The first is the PPO penalty method. This one uses the Kullback-Leibler KL divergence, which, as you might recall, is a way to measure how different two probability distributions are. Here it measures the difference between the action distribution produced by the new policy and the old policy, the policy before the update.
And how does the penalty work in practice?
It adds a penalty term to the objective function that increases if the KL divergence between the old and new policies gets too large. If the update tries to push the policy too far away, this penalty term kicks in and effectively discourages that large change, pulling the update back towards the old policy. It acts like an adaptive leash.
Okay, that makes sense conceptually, but the sources seem to imply the second method, PPO clip, is more commonly used. Why is that?
Yeah, PPO clip tends to be simpler to implement and often performs just as well or even better in practice. It achieves the control in a more direct way using clipping. It starts by calculating the probability ratio, often denoted R theta. This is simply the probability of taking the chosen action and state tealer under the new policy, divided by the probability of taking that same action under the old policy before the update.
So, a Frappy style is the ratio is 1, the policies agree. If it's 2, the new policy is twice as likely to take that action.
Exactly. Now, PPO clip introduces a clipping function. The objective function involves the term A theta times at 3, the ratio times the advantage. PPO clips this ratio to stay within a small interval around 1. Specifically, it uses 1 epsilon, 1 plus epsilon, where epsilon is a small hyperparameter typically set to something like 0.1 or 0.2.
Okay, wait, so it calculates the ratio, but then it forces that ratio to stay within the range $1 epsilon, 1 plus epsilon, before multiplying by the advantage. What does that achieve?
It puts a hard limit on how much the objective function can change due to a single action's contribution, regardless of how large the advantage equalus is. If the ratios is greater than $1 plus epsilon, meaning the new policy strongly increases the probability of an action that had positive advantage, the clipped value is capped at $1 plus epsilon dollar. This prevents the objective from getting excessively large just because the policy changed a lot. Similarly, if the ratio is less than $1 epsilon, meaning the new policy strongly decreases the probability of an action that had negative advantage, the clipped value is capped at $1 epsilon. This prevents an overly large negative contribution. PPO actually takes the minimum of the original objective term and the clipped objective term, 1 epsilon, 1 plus epsilon, ensuring the update size is constrained.
Ah, okay. So it's basically saying we want to follow the advantage signal, but we absolutely refuse to let the policy change by more than this small epsilon factor in one go. It prevents the policy from running away with itself.
That's the essence of it. It's a very elegant and practical way to enforce that proximal update constraint, ensuring much more stable and reliable training. You avoid those sudden performance drops that could plague earlier methods. And it's this combination of strong performance, relative simplicity compared to TRPO, and that crucial stability that has made PPO such a workhorse algorithm for complex RL tasks, including the kind of demanding applications we see in cybersecurity. Hashtag outro. So we look back at the journey we've taken today. We started right at the foundation, the mathematical necessity of the Markov decision process, how framing the problem with states, actions, transitions, and rewards, and crucially, leveraging the Markov property to focus on the present makes learning feasible. Then we looked at the core ways an agent can actually learn, directly learning a policy, the how-to, learning a value function, the rating system, or even building a predictive model of the environment itself.
Right. And then we saw the evolution needed to handle real-world complexity. Deep Q networks brought in neural networks to approximate those Q values, crucially using the replay buffer to break data correlations and stabilize training. Then, ADC took it a step further, separating the actor, policy learner, from critic, value estimator, and introducing the advantage function as that vital variance-reducing baseline signal for guiding the policy updates.
And finally, PPO delivered that last essential piece for truly scalable and reliable learning, maximum stability. By using that clever clipped surrogate objective, PPO ensures that policy updates remain controlled and proximal, preventing the kind of catastrophic performance collapses that could happen before. It keeps the training process on track, even over long runs and in complex, noisy environments.
And really understanding this whole progression from NDPs through DQN, A2C, and PPO allows you, the listener, to really grasp how AI agents can be trained to perform sophisticated cyber operations. Whether it's finding the optimal sequence of steps for network reconnaissance, automating the testing of vulnerabilities, or simulating realistic adversary behavior for training defenses, it all comes down to agents learning to maximize that discounted future reward within the MDP framework, powered by the representational capacity of deep learning and refined by algorithms like PPO.
Which leads us perfectly into that final provocative thought, stemming directly from some advanced applications mentioned in the source material. Researchers working on complex multi-agent systems found that even combining A2C with a sophisticated setup called a double-agent architecture DA-A2C, they still ran into significant convergence problems. Training was often unstable, taking maybe 30 minutes or more to get reliable results, but when they simply swapped out A2C for PPO in that same architecture, creating DA-PPO, the stability improved dramatically. Models converged reliably in under 10 minutes. So the question is, if PPO's foundational stability unlocks the ability to reliably train RL agents on network simulations involving thousands of nodes, something previously plagued by instability, what currently intractable cyber defense challenge, one that demands both massive scale and rock-solid training stability, might this breakthrough finally allow us to tackle next?